So in this video, I'd like to talk about synthetic routes. All right. Basically, what a synthetic route is a plan that you can make in order to make a desired organic molecule. All right. One of the things that they expect you to know in the IB curriculum is that, first of all, that when you have a desired molecule, a lot of times it takes more than just one step to make that molecule. And there's some strategy involved in how you do it. And in general, it's best to do it in a way that gets to your desired target molecule in the fewest number of steps. All right. So why is it generally advisable to do it in the lowest number of steps? All right. For example, if you were to want to get to, let's say, target D, would it be better to go from A to B to C to D? Or would it be better to go straight from A to D? All right. Basically, what this is saying, it's better to go straight from A to D because you end up running into problems with each time you have to perform a step. So some of the things that so one thing that inevitably happens is that in every step of a synthetic sequence, you're going to end up losing some of your material. All right. In an ideal world, if you started with 100 molecules of A, you would be able to make exactly 100 molecules of B. But in reality, that's not the case. And so a couple of reasons for that. One reason is incomplete reactions. All right. So let's say that you want to turn A into B. All right. And that A is your starting molecule. All right. Well, ideally, you would be able to, if you started with 100 of these, you would be able to get eventually get 100 molecules of C if your reaction was complete. But as you know from previous unit, sometimes reactions are reversible. All right, and so sometimes you're doing a reaction and you try to get it to make as much of the products as possible, but for whatever reason it stops. All right, well, if that happens, some of the molecule that you're trying to make you can't get. All right, so maybe if there was theoretically, if you had like 100 of these, if it went to 100% completion, you would get 100 of these. All right, but in reality, it might stop where you get 90 of these and 10 of these. All right, in the real world, you just have to stop there and just accept that you're not going to get complete conversion. All right, so again, this is majorly going to be true whenever you have a reversible reaction. All right, another problem that you run into is side product production. All right, so let's take this reaction for example. Let's assume that we wanted that this was our desired product molecule. All right, and this is the reaction. This would be this is a radical halogenation. We covered this back when we were doing alkanes. All right, the thing about this desired reaction is that it results from the radical reaction between this methyl radical and a chlorine molecule, creating this right here. But if you recall, there's several possible side reactions that can occur. So let's even in our desired reaction, we end up having this methyl radical. Well, one thing that can happen is two methyl radicals can combine like this, and remember, this is what's called a termination step when you're doing a radical reaction. All right, now termination is when two radicals just pair up to make something which is not a radical. All right, but this is something that can happen. All right, and it does happen. And the problem is that this is not one of our desired products, but it consumes some of our starting material. All right. Another possible side reaction is, let's say that we get our desired product, and it's still in the reaction mixture, and it reacts with this chlorine radical to that would make this radical right here that could react with another molecule of chlorine and through this mechanism right here, and we could end up getting this product right here. All right, so even though this might be what we want to make, all right, the reality is when you do chemical reactions, sometimes you get undesired side reactions. All right, and again, every reaction that you're doing in your sequence, there is a potential for this to happen, and generally that's going to involve loss of some of your products. All right. Another issue is difficulty in isolating products from the reaction mixture. All right. Remember, when you're doing a reaction, you first of all, a lot of times you're dissolving it in a solvent. That's where the reaction occurs. It's not like the reaction isn't happening to the solid material. It's happening to the material dissolved in some solvent. All right. And also, when the reaction is done, you're going to have some byproducts from your reagents. All right. For example, when we were talking about reductions and oxidations, if you use sodium borohydride, well, it's not like the sodium after the reaction done, there's nothing left over. All right. Generally, there's going to be some inorganic byproducts, and when you're done, you want to get your desired product away from all this solvent and all this byproduct material, so that you just have your desired product all by itself. All right. And so there's a couple ways that you can do this, but generally what you call the material once you get it all by itself is the crude isolated product. All right. And crude just means impure. All right. Which leads us to the next problem that can cause loss of some of your chemicals, which is loss involved in purification procedures. All right. So even if we get our desired product away from the solvent and most of the other byproducts, generally it's not going to be 100% your desired product. All right. So you might have your product. We'll just say that our product is A, but B is just some impurity. All right. Something that's not what we want. All right. Well, what we want to do is we want to get a purified product. All right. And a purified product would just be nothing but the compound that we want. All right. Well, generally there's a couple different procedures that you can use to clean up your crude products. All right. Distillation is an example that we showed earlier this year. Another example is column chromatography. In organic chemistry, a lot of times that's silica gel. I believe I showed an example of that earlier this year also. So the thing is, no matter what procedure that you're doing to purify your product, generally there's going to be some loss of your desired material. All right. So in the process of trying to get A all by itself, well, yes, you can see here that we did get rid of the impurity, but we also lost one of our desired products. All right. And so the overall result of all of these technical realities is that when you're designing a synthesis, in general, you would like to try to do it using as few steps as possible. The fewer steps you have, the fewer chances for these realities to cause loss of material. Right? That's possibly a little oversimplified. In the real world, sometimes cost matters. All right. Sometimes percent yield matters. Sometimes if you get high percent yields in a 4-step procedure, that might be better than a 3-step procedure where you get low percent yields. But that's probably a little bit more than what you need to know right now. So one thing that the IB curriculum holds you responsible for is applying certain reactions towards making products. All right. So the first one that they mention, although it's not really useful as a synthetic reaction, is obviously to know that either hydrocarbons or alcohols can be burned to make carbon dioxide. All right. Again, they mention this as a reaction that they mention it in the synthetic roots chapter, but it's not. Again, combustion's not really that useful as a synthetic reaction, all right? Because it only ever makes two products, all right? First reaction that you should definitely make sure you remember is radical substitution of alkanes with halogens, all right? Remember that's would be a reaction such as this, all right? You're also responsible for knowing addition, any type of addition reaction to an alkene, all right? And remember, there's 4 of those that we learned. Hydration, hydrogenation with either a palladium or a nickel catalyst. This would be halogenation, and this would be hydrohalogenation. All right. So, You're also responsible for substitution reactions with sodium hydroxide. So the two versions of that we learned about were SN2, where generally SN2s are when you have a primary halogenoalkane, all right, or an SN1, where that would typically be either a secondary or a tertiary halogenoalkane. All right, and remember, for SN2, you're generally going to want a solvent such as DMSO. All right, for an SN1, that reaction is favored with ethanol. We covered that a few videos back. Another reaction you need to know are nitration of benzene. All right. One reaction we have not covered yet, but one that you're responsible for knowing, is that nitrobenzene can be reduced to an amine through a two-step procedure. All right. The first step is treatment with tin metal and hydrochloric acid to make this compound right here. This is just the ammonium version of the amine. All right. So one way you can say this is the conjugate acid of this amine right here. All right. So if you wanted to get to the what you would call the free base, or the free amine, is that you treat it with some base, or such as hydroxide, to give this amine. All right. So you're not responsible for knowing the mechanism of this reaction, but just know that it can be done. All right. One thing that we talked about a while back is oxidation and reduction, going from alcohols, aldehydes, carboxylic acids. You should also know, I should have added ketones here as well. All right. Some of these, some of the reducing agents we talked about were lithium aluminum hydride and sodium borohydride. But then there's also there's the oxidation reagent, which is acidified dichromate. So, and again, you can refer back to those videos if you need details on these exact steps right here. And the last reaction that you're responsible for is esterification. All right. So, just as an example of a type of question that might involve a synthetic route, all right, would be to suggest a route to make this compound right here, which is called ethyl acetate, starting from ethene. All right, so ethene, remember, is just two carbons double bonded to each other. All right, so generally what you do is you start with what's called a retrosynthesis. And all that is a fancy way of saying start with what you want to make and work backwards. All right, well, if this is what I want to make, well, so and a lot of times you'll see this kind of arrow right here. It's the two lines with the big arrow. This means, hey, I'm planning my route from what I want to make and kind of breaking it apart and going backwards. Well, this could be made from, I could see this could be made from a carboxylic acid here and an alcohol right here. All right, so let me draw what those things are. And then let me think, all right, could I could I make those? How could I make those? All right, and I can see that, although I didn't draw it here, these can both be made originally from ethene. All right, so how are we going to do that? All right, so this is, we take ethene, we can perform a hydration on that. All right, if we hydrate it, we'll end up getting ethanol right here. Although, if you wanted ethanol, this is not the way that you would do it. You would do it by fermenting corn. That's the way it's done in industry. Let's save some of this. But let's also take some of this and let's oxidize it with that should be chromium. That should be Cr207. So we could oxidize to make some of this right here, which would be, this is acetic acid. All right. So, so taking this compound right here and taking some of this right here, these are now this is now the carboxylic acid and the alcohol that are needed to do an esterification reaction to give our desired product. All right, so notice we didn't get to our desired product in one step. It took a couple of steps, but just using a couple of simple reactions, you can construct a lot of desired molecules. All right, so we'll practice synthetic routes a little bit more, and hopefully it will become easier with practice.